It's a great honor to start this session. Thank you for this opportunity. And today I would like to talk to you about new ion trap that we developed in Brian Chait lab at Rockefeller University. We developed this ion trap to enable parallel mass spectrometry, but it also has numerous applications. And today I will focus on one, how we use this instrument to improve signal-to-noise of the mass spectra. I would like to start with a simple question. What is in common between the way we sample ions for MS and scooping Niagara Falls with a bucket? One simple answer is both activities are equally inefficient. For example, typical ion currents that come from current modern ion sources can go way beyond 10 power 10, 10 power 11 ions per second. And yet we take only a small portion of these ions for mass spectrometry for a variety of reasons. It can be some charge limitations of trapping devices, or it could be duty cycles, selection and ion selection, ion rejection, variety of reasons. This is why the lots of efforts to improve the situation, lots of efforts put to make mass spectrometer faster and reduce the overhead of MS analysis. Another opportunity is to take ion beam and split it into sub-beams containing ions from non-overlapping MOSZ regions and apply parallel MS, and I will talk this in the end of my talk. And yet, one more opportunity is somehow reduce this number of ions in a meaningful way and sample only useful ions for mass spectrometry. Typical ion sources produce ion charges in different charge state. We and others showed that ions in a charge state +1 frequently contribute to the chemical noise background. So sometimes it will be advantageous to remove these ions from the beam. If we're interested, for example, in analysis of chemically cross-linked peptides, it could be further advantageous to remove ions in a charge state +2 and +3. Such focused sampling of ions in the context of the problem we're trying to solve may greatly increase signal-to-noise of analysis. And we have built an instrument that does exactly that. It allows us to deplete low charge state ions as it goes from the ion source to the beam. We call this mass spectrometer, we call this ion trap multi-quadrupole ion trap, or MultiQ-IT for short. We have built several versions of this device and incorporated it in electrospray source between electrospray interface between electrospray source and LCQ-DECA, old instrument that we merely use as an ion detector. So ions passing through the electrospray source, through the heated capillary into a quadrupole ion guide, go through the skimmer in a constant fashion and fill in MultiQ ion trap where ions reside for some time and freely flow towards LCQ-DECA to be detected. Sometimes we pulse ions into MultiQ ion trap, and I'll show you one example where we used pulsing to determine resident lifetime of the ions in this ion trap. We also measured the ion currents that go through major elements of ion optics here and deduced that 10 to the power 9 charges per second go through the MultiQ ion trap. So we use this device to deplete singly charged and low charge states in a spectra. Let me show you an example. Here's the spectrum of 5 peptide mixture. Major peaks are labeled here. For example, P1 is a peptide 1, P2 is peptide 2, etc. Peptide 1 is a glycine and cephalin singly charged species. And in the range from 500 to 600, you can see 5 peaks. That's very convenient for us because they represent each peptide in a different charge state. If we set MultiQ ion trap to operate in single charge ion depletion mode, interesting things happen. First, the spectrum becomes much cleaner because we remove majority of single charge peaks from it, or reduce their intensity in the spectrum quite considerably. And if we look at their range from 500 to 600, we see that a peak of lysine and cephalin singly charged species was reduced by more than factor 54, while higher order charged state peptide didn't change their intensity dramatically. Here's an experiment we made with Brian Chait, who is starring in a movie that demonstrates how easy it is to switch between two modes, depleting and not depleting. Please pay attention to this group of peaks. It's again these 5 peaks. This is charge state +2, +4, +1, +3, and +5.
Ready?
Yep.
I'm switching now. Switching. See that, my young friends?
Switch it back.
Unlike me, your fingers never leave your hands.
Wow.
So anyway, this mode is very useful, especially when we analyze very small amount of samples. For example, when we diluted this 5-peptide mixture 100-fold, we couldn't detect peptides, but only prominent peaks that frequently associated with impurities, frequently formed by clustering of water with methanol and metal ions. But when we set MultiQ-IT trap to operate in a single charge depletion mode, we were able to detect all 5 peptides in the spectrum. Depletion mode also useful when we analyze spectra of proteins. For example, this is spectrum of myoglobin obtained from the solution containing polyethylene glycol, which is frequently used as preservant, protein preservant. No spectrum of myoglobin observed under this no depletion conditions. But when we set MultiQ-IT trap to operate in depletion conditions, we were able to detect peaks of myoglobin. We couldn't reduce completely the peaks of polyethylene glycol, singly charged, but at least we reduced them considerably to the point where their contribution to the total ion signal was small enough to increase signal-to-noise observation. Is it possible to deplete single ions in a charged state 1+, 2, and 3+? Indeed, we found a new effect while we were measuring total ion current of electrospray spectrum of 5-peptide mixture again. But this time we were operating LCQ DECA as fast as possible in a turbo scan mode that allows us to obtain 5 spectra per second. And we needed this speed because what we thought to do is we wanted to block ions coming into MultiQ-IT trap and see how quickly the ions that already in MultiQ-IT trap will leave the device. So indeed, we block their ions flow into MultiQ-IT trap by raising some potential and observed exponential decay of the ions with their half-life time, resident time, 300 milliseconds. But what's more remarkable is different ions leave MultiQ-IT trap at different rates. For example, ions in a charged state +1, +2, and +3 leave very quickly, and by the time, and after 1 second after the pulse, majority of these ions left ion trap. But that's not true for highly charged state that still reside in MultiQ-IT trap and need more time to leave the device. Now we exploring the utility of this effect by sampling later fractions to determine the positions and signals from the high charge state peptides. In order to explain how this MultiQ-IT trap works, let me start with explaining how we start building it. We still learn how to do that ourselves. So we start with the cuboid. It can be parallelepiped or some higher order polyhedron. We put small cylindrical electrodes in arrayed fashion on supporting plates. And here's MultiQ-IT trap 486 version, the latest version that the results I showed you, being in the process of assembly. We finish the structure by putting the front and the rear plate, and that creates the volume encompassed by array of electrodes, which is capable to hold ions when appropriate RF and DC potentials are applied to this structure. it is convenient to think about the structure in the number of electrodes we used along single dimension. For example, in this example, there's n equals 6 along single dimension, and one can show that we need only 152 electrodes to finish the structure, and that will produce 150 quadrupoles. For example, for the latest version, MultiQ-IT trap that I used for experiment, n equals 10, and that creates 486 quadrupoles. A number of multiplicity of quadrupoles is a very important parameter, but because it creates multitude of ions inputs and outputs to exit and enter the device. For example, here I just showed you 2. But for example, for ion depletion, we use all of them, and I'll explain it in a minute. Here's the ion motion and trajectory computed in such a device. You can see that a single charge ion with the parameters indicated can stably maintain. This is for more than half a second. And interesting happen, if we reduce RF potential from 150 volts to 50 volts, ions start exploring bigger volume inside such a device. And occasionally, visiting the spaces between the quadrupoles, because at that parameters, they have stable trajectory in the quadrupole, along the quadrupole axis. And eventually, they may leave the device. For example, here, there's a calculation for 200 ions that explore this volume, and eventually leave along the axis of the quadrupoles. And this ability of ions to live along a multitude of quadrupole axes can be used to a high advantage. First of all, it can be used for online charge depletion. Charge depletion was first shown by 3 groups. 2 groups from SAIX, one Jim Hager, and another Chernyshevich et al., and the 3rd group from Tolmachov from Dick Smith lab. Let me illustrate briefly the idea behind this on using just one quadrupole, but don't forget we have multiple quadrupoles. It's just one of the quadrupoles that I will be using for explanation. So the main interplay happens between offset of the quadrupole and the plate. If there are potential difference is high, for example, 3 volts, that will push positive ions back towards the center of MultiQ-IT trap, where they will be stably maintained for a long time. However, if we reduce this potential to a very small value in the order of kT, 30 electron volts, interesting things happen. Ions that thermalize by that time will have energy comparable to kT, where K is Boltzmann constant and T is temperature. So single charge ion will see the barrier with the height almost non-existent height, because they have kT kinetic energy and the barrier height will be kT. So they will easily leave the ion trap. But we cannot say this for multiply charge ions that will see the barrier proportional to their charge. For example, doubly charged ions will see the barrier as 0.6 electron volts, and triply charged ions will see the barrier as 0.9 electron volts. And that creates the possibility to get rid of singly charged ions and increase the probability of leaving them from the device. Now we have 485 quadrupoles to play with, so for ions actually to explore and exit. And that multiplies the effect to the point where we observe it in real time as ions enter and exit the device. If you allow me to compare this to something that already exists, I would throw a comparison to online dialysis. Here we, of course, however, we can control the pore size by just simple electrical potential. But our ultimate goal is to use multiple ability of ions to exit through the quadrupoles. To split ion beam into sub-beams containing ions from non-overlapping M over Z regions. And that can be achieved by setting some of the quadrupoles to operate as mass filters. In this case, we can enable parallel MS analysis. In this parallel MS analysis, we start with ion beam. We split ion beam into sub-beams containing regions of ions, non-overlapping regions of ions, and towards which we apply high-performance, array of high-performance instruments. For example, array of FTR cells that was beautifully shown in James Bruce group from Washington University. Or we can use ion traps that were developed by array of ion traps that were developed by Graham Cook's lab, or array of RB traps, or a single multi-beam time-of-flight mass spectrometer. One can show that result obtained by this using parallel approach will increase speed and coverage and depth of analysis n-fold, whereas n is a number of parallel channels, simultaneous parallel channels in which we analyze the ions. Such approach was successfully used to revolutionize parallel DNA sequencing and parallel computing. And now we would like to bring this to mass spectrometry using MultiQ ion trap. In the future, we currently develop a tandem MultiQ ion trap, and which we put in the front of RB trap. We persuade two goals, major goals. One goal is, can we obtain depletion coefficients equal to a few thousand? Why? Because this is quite independent devices, and we assume that we have hypothesized that we can obtain total depletion coefficient as a multiple of depletion coefficients of each device. And remember, we got depletion coefficient around 50. So would we be able to get 2,500? And the goal of this exercise is to tremendously improve sensitivity of a mass, at least in some cases, when we're interested in multiply charged species. And there are tons of problems like that. And the ultimate goal is to add actually several quadrupoles between these devices and split ions that say come in through this quadrupole into multiple subbeams, concurrent subbeams. And that device will just allow us to test this possibility. But our ultimate goal is to produce parallel device for parallel, enabling parallel MS. Finally, I'd like to thank all members of the Chait lab that helped me to prepare this talk. I'd like to thank Gordon Chait, who edited the video that I showed you today, and I thank you for your attention.
Well, thank you. That was a very interesting talk. Is there any questions for our speaker?
Yes. Well, thank you very much for your talk. It's amazing.
Thank you.
So the question is, can you do the other way around? So instead of depleting M+2, +3, +4 ions, actually focus like +1 ions?
Yes, we can.
Okay.
I just didn't want to complicate, but yeah, we found conditions where we can enrich singly charged ions versus multiply charged ions by actually reversing this small potential to slight negative, and it sucks out more readily multiply charged species than single charged. But we didn't investigate this yet in detail.
Thank you.
I have one question. How long does it take from the time you say, okay, change, to you actually change what's coming out? Is this chromatography time scale, or is it much slower?
It's a fraction of seconds.
Fractions of seconds?
Seconds, fractions of seconds.
Interesting. Thank you.
Thank you.
Well, I'd like to thank our speaker once more time.